Hello everyone, we are Team 8 and today we'll talk about algorithm design, sorting algorithms, as well as recursions. Our team member includes Lê Đức Huy, Quang Nguyễn, Đoàn Đức Hiểu, Nguyễn Minh Nguyễn, and Đoàn Duy Bảo Khá. So first, I'll talk about algorithm design for motivational example. Let's say you are trying to look for a specific book within among thousands and thousands of books. You can go around it, go by looking through each and every one of them, but that would take forever. So you would try to come up with a clever strategy to quickly narrow down where the book might be. That strategy is what we would call an algorithm. So algorithms are basically step-by-step procedure to solve problems efficiently. And let's talk about some common strategies used to create algorithms. First off, we have the brute force strategy, which means trying all possibilities until a solution is found. For example, you're guessing a three-digit password, you can try 000, 001, 002 until the solution is found. And then you have divide and conquer, which means breaking the problems into smaller subproblems, solving each, and then combining the result. A classic examples for this would be the merge sort and the quick sort. Next up, we have the greedy algorithm, which means making the best choice at each step to eventually reach a global solution. Example, when trying to, let's say you're trying to give exact change with coins, you will always pick the largest coin available first. Let's say you're trying to give an $0.85 change, you would start with the 50-cent coin, then the 25-cent coin, then the 10-cent coin. And finally, we have dynamic programming, which means solving complex problems by breaking them into simpler overlapping subproblems, storing the results to avoid repeating work. Here's a quick example of a dynamically programmed function that calculates the Fibonacci number. You will study this in the upcoming recursive part rather than right now. However, this version is slightly different from the basic recursive approach because it memorizes previously computed function calls to avoid repeated work. So yeah, just note that down for now. Next up, we have complexity and big annotation. So algorithms have efficiency. Even for the same problem, you can have many different solutions and you can have many different algorithms dedicated to it. Each algorithm gonna have its own efficiency and complexity. And complexity as in time complexity, how long it takes to run the algorithm, and space complexity, how much memory the algorithm uses. So how do we effectively represent this complexity? We use the big O notation. So for this specific part, let's say time complexity, right? So O1, constant time. An example would be accessing the first item within a list. So even your list, right? Even if it increases in size, if it has n elements or n square elements or n plus one elements, it's still going to take the same time to access the first item within that list. So it is always a constant time. It is always an O1. Then you have ON, which is a linear time, which means time grows linearly as the input grows. An example would be searching for a number within an unsorted list. As you can see within the code below here, the loop would check every single element once. So that'll be n steps if the list has n elements. So that'll be ON. If the list increase to 2n, that'll be 2n steps. If the list increase to n plus 1 elements, that would take n plus 1 steps. Simple stuff. And ON square, which is quadratic term. Example would be comparing every item in a list with every other item. So as you can see in the loop, in the code here, I used two for loops. So similarly to the last example, the outer loop would also run n times, and for each iteration, the inner loop would also run n times. Thus, n multiplied by n would be n squared times O n squared time complexity. So how do you check these algorithms? You can count operation in your code. You can analyze loops and recursion depth. You can observe runtime for different input sizes, or valid methods and steps toward calculating the algorithm efficiency. One specific example to help you better grasp the idea. Let's say you're trying to find the largest number in a list. One method is to approach it linearly. You can check each number one by one. So that'll be a when time complexity. Or you can, another method, you can sort it first, then pick the last element. So as you can see within this code here, the sorted method would use team sort, which will be a O(n) log n time complexity, and accessing the last element would be an O1 time complexity. So the total time would be O(n) log n plus O1, which is still going to be O(n) log n. So even for this very simple problems, you can have multiple solutions with different efficiency, and that really goes to show why algorithm design matters. Yeah, and that concludes my parts for now.
Let's continue with sorting algorithms. Think about that you're creating your own Spotify playlist, and first it only includes 10 to 20 songs. So when you want to find certain song, you can just scroll up or scroll down to find one or two times. However, when you host the longest playlist on Spotify, 10,000 songs, that is impossible, and sorting will help you in this situation. You can sort the song's name in alphabetic order so that you can find easier. So sorting is like organizing your data so it's easy to search and process. This is the definition of sorting. Sorting is the process of arranging items in a specific order, usually ascending or descending. There are some common sorting types like selection sort, merge sort, quick sort, purple sort, and so on. However, in this presentation, I will just go through these three types of sorting. But before that, I want you to know that why sharing is important. It's because it makes sharing faster, help analyze data efficiently, and is needed in real-world applications like ranking, scheduling, and organizing databases. Let's continue with different types of sorting, but I want you to know that all the examples I show later, I want to sort in ascending order. So first, selection sort. This algorithm looks for the smallest elements, place it at the beginning and repeat. For you to understand more, I have this sequence. I will look for the smallest element, which is 1, swap it with the first element, and I will get this new sequence. This sequence includes two parts. The first part is one is charted, and the remaining is the uncharted part. So I will do continuously those steps with the uncharted part until I get the sequence that only includes charted part. This algorithm is simple but not very efficient for large datasets, with time complexity is big O n squared. Next, I have merge chart. This type of chart uses the divide concur algorithm that we have shared with you before. So I will split the list and its sublist until those sublists only include one element. Because of that, those sublists are shorted. Then I will do the merge step, and finally I will have the shorted version of the original list. This algorithm is efficient and stable with time complexity being O n log n. Last but not least, I have quick sort. I will pick randomly a pivot, partition the list into numbers smaller and larger than the pivot, then do the same thing with the smaller and the larger part until I have the shorted version. This algorithm is fast in practice with average complexity being O and log n. However, because I pick randomly, so in the worst case, I might pick on the pivot be the smallest element. This makes quick sort turn into selection sort with time complexity being big O n squared.
Alright, so since we have already learned about selection sort and merge sort in class, today I will be teaching you how to do a quick sort. So quick sort works by selecting a pivot element from the array and partitioning the other element into two subarrays based on whether they are less than or greater than the pivot. The subarrays are then recursively sorted. We are going to make a function called quick sort, which take a list as the parameter. The base case will be when the length of the list is less than or equal to 1, in which case the list is already sorted, so we just return itself. So there are actually quite a few ways to choose the pivot element. Some people choose the rightmost one, some will choose a random one. So for this version, I will just keep it simple and choose the first one, which will be the first element of the list. All right, so as I mentioned, we will divide the list into three smaller lists. So the first one, which I will call left, will have all the elements that are less than the pivot, excluding self. So it will be x for x in error if x is less than pivot. The middle one includes the pivot itself and all values equal to it. So it will be x for x in error if x is equal to the pivot.
And the last one I will call right equal to all the elements that are greater than the pivot. So equal x in error if x is greater than the pivot. All right, now let's make the recursive call. The left and right sides of the list are obviously not sorted yet, so we return quick sort of the left plus the middle one and the quick sort of the right one. And that's it. The function is finished. But if you are still a bit confused, here is what the recursive step really mean. So the middle list is always in the correct position, obviously, so it really doesn't need any sorting. However, the left and right list may still be unsorted, so the same process is repeated on them. Each recursive call keeps breaking the list into smaller parts until everything is reduced to the list of size 1 or 0, which are obviously already sorted. When all of the sorted pieces are combined back together, the entire list becomes fully sorted. So I have a visual explanation right here in case you are still confused. As you can see, the list will be split into three parts. However, since the middle part doesn't require recursive call, you will only see the left and right side right here. The left side include all the elements that are smaller than the first value of the list, which in this case only have the number 1. However, the right side of the list include all the larger element and have 3 elements inside it. So since 3 is obviously larger than 1, it is break down again and fits back together to form a sorted list, which you can see right here, which is 568. It then went all the way up to form a sorted list with 1, and you can see that the function returns the list of 1, 2, 5, 6, 8, which is a sorted list. So at every step, quicksort must look at every element once to split the list, which takes O n time. And since when it is pieced back together, it takes roughly O log n time. The the average time of the quicksort algorithm take O n log n time. However, quicksort can become O n power of 2 in the worst case. This happens when the pivot is always the smallest or largest element for every recursive call, causing the list to shrink by only one element each time instead of being split in half. In that case, the algorithm ends up doing O n power of 2 times.
Hello, today I will teach you about recursion. For an example, let's take a look at this list of code. As you can see here, since I'm live streaming the stream itself, the stream keep on repeating itself seeming infinitely until it reached a point I can't even see what it is at the end. This is recursion. So what is the definition of recursion in coding? Basically, it's a function that calls itself. While the definition itself seems quite simple, implementing it can be quite a headache, especially for a beginner. A recursive function has two key properties: a base case, which is a stopping condition and prevent infinite recursion. In this factorial function right here, the base case is n equals to 1, which means that the recursion will end when n equals to 1. And a recursive call, which reduces the problem size every time it's called. In this function, you can see that the recursive call is at the very end, which calls the function itself, but reduce the parameter by 1. And what happened in recursion? To show you how recursion actually works, I have a visualization right here. For our first recursive function, I will write a Fibonacci calculator. Now, the cool thing is we can solve this really elegantly using recursion. Here's the idea: if n is 0 or 1, we will just return n, and that's our base case. Otherwise, we will return fifth n minus 1 plus fifth n minus 2, and that's our recursive case where the function calls itself. The logic behind this is simple. To find the n Fibonacci number, we can just calculate the sum of the two Fibonacci number behind, which is literally the definition of the Fibonacci sequence. And now look at the graph here. We can see that the function keeps calling itself with a smaller variable until it's reached the base case, and which is 0 and 1 in my example. And once the base case is reached, the stack starts to unwind and adding the results together, and eventually we get out the answer of fine. And to show you how why the base case is very important, if I comment out the base case and run the same function, the program would keep calling itself over and over. and never stop. And you can see in the video, the function exists, the limit of 256 calls and crash. Similarly, in Python, the stack overflows and crash. That's why the base case is crucial in recursion. Now, to compare between the recursion and linear algorithm, like iterative approach, again, we use the Fibonacci function as an example. Using recursion, the code is very clean and easy to read. You just define the base case and recursive case, and the function call itself to solve smaller pieces of the problem. It mirrors the mathematical definition exactly, but there's a catch. The recursive function can be less efficient. Every function calls take up memory on the call stack, and in some cases, like Fibonacci, we end up calculating the same value multiple times. That's why a recursive Fibonacci function has an exponential time complexity. Now, if we switch to a linear iterative approach, we would use a loop and store the previous value. The code might be slightly longer or less elegant, but it's much faster and use less memory, especially for large input.
Alright, so to make it easier for you guys to visualize how recursion actually works and to show how the same function can be written both iteratively and recursively, I will now turn the normal binary search into a recursive one. So if you look at the normal iterative version, you will notice that the function keeps on running as long as that is less than or equal to the end, or the middle value of our search range is the target. This will be our base case. And in the iterative method, you can also see that there are two main scenarios in here. So if the target is less than the middle one, we will cut the list in half and keep the left side. But if the target is greater than the middle value of our search range, we will also cut the list in half, but this time we will keep the right side. These two cases will become our recursive calls. Alright, so now that we already have the base case and the recursive step, we can kind of visualize how the recursive function works. So first, I will make a function named recursive binary search, and we will actually have 4 parameters, which will be the list itself, the target, the starting point, and the end point. Alright, so now I will create a variable named middle, which will just be the mean value of the start and the end. Alright, we will start off by writing our base case. So first, if the middle value of our search range is equal to the target, we will return it. And if start is greater than the end, we will return -1, which simply means that the value does not exist in the list. Alright, so now it's time for the recursive call. So if the target is greater than the middle value, we will simply call the function again. So return recursive binary search for the list, the target. But this time we will update the left boundary to be middle +1. And the answer to the same. Now but if the target is less than the middle value, we will also call the function again, but this time we will update the right boundary to be middle -1. List the target, the left side, and middle -1. And that is basically it. Now, alright, so I will just make a random sorted list so you can actually see how it works. So I have a random list, will be something like one. I'm trying to make it so that it is kind of sorted in itself. Alright, so if I input the random list I have here into the function, actually let me print that. Alright, so I'll input this. Our target will be something like maybe a 9. The start will obviously be 0, and the end will be the length of the list. -1. Alright, let's run this. All right, so you can see that it returns the number 4, which is exactly the index number of our target in the list. But if I input something that the list doesn't have, maybe something like 91, it will return -1. So which means our binary search is working. Thank you for watching.
Now I will introduce you guys to the two most common forms of recursive functions, which are tail and head recursions. For tail recursion, the recursive call is the last statement in the function, which means after all computations are finished, the functions just need to return the result of the recursive call. So there are no pending operations whatsoever that need to be done after that. And for head recursion, a recursive call is made. So this recursive call is prioritized before any operations are made in the function. So the function will call itself to solve a sub-problem, then compute the result. Now I will showcase some examples from the two different types of recursions. For tail recursion, I have a case, a factorial problem here using tail recursive functions. So you notice that I have two arguments with its n variable and accumulator equal to 1. So the recursive call for tail recursions will be the last actions. So when I call factorial tail 5, it will call itself 5 times. But the recursive calls will not be stacked. This is because of the accumulator. The accumulator will take the result from the first, will save the result from the first call and before multiply with the next recursive call. So eventually it will continuously multiply until it reaches the base case, which is n equal to 0. So when n is equal to 0, the accumulator equal to 120. So we can take this value as our final result. And this is a similar case, similar problem, but now we're gonna use head recursion. So in head recursion, the recursive call happened first. You can see that we're gonna have a recursive call placed before we process with the result. So when we call this function factorial head 5, similar to we call 5 similar to the tail recursion, it will eventually stack until it's reached the base case because the call it doesn't have any available values to be compute. It is only have the value of 1 until the recursive call have n equal to 0. So when the smallest case has the smallest value is 1, return to the bigger call, it will calculate it, and then step by step it will go through to every other bigger call until it reaches the final call that we have, which is factorial head 5. So when we already have this value, we just need to multiply that value with n, and then we return that value, and which is equal to 120. So yeah, that's how we gonna solve this problem using head recursion. So what are the differences and similarities between tail and head recursions? In other programming languages, tail recursions are always better. This is because of a thing called built-in TCO. So built-in TCO is a built-in method that optimizes space complexity for tail recursion. So standard Python does not support built-in TCO unless you can build your own TCO method that help to reduce the space, memory, the stack of tail recursion. Then tail is more efficient than head recursion. But in general, they have the same time and space complexity. The only difference is the recursive call. For tail, the recursive call execute last, and for head, the recursive call execute first. I think that's all you need to remember for recursive functions in Python. So basically, last but not least, when to use recursion. So recursion is really powerful for some problems that are naturally hierarchical or self-similar. For example, divide and conquer algorithms, merge sort, quick sort, where the problem splits into smaller subproblems, tree and graph chisels, where each node can have multiple branches and you want to visit them all. And fact-checking problems like find all the possible paths in a maze, solving Tower of Hanoi. Yeah. On the other hand, if the problem is not that difficult or it can be solved easily with a loop, just use a loop. That's just more efficient in terms of time and space complexity. So the key takeaway is use recursion when it simplifies the problem and matches its natural structure. But you must be careful of the efficiency and the stack usage, or else there will be a recursive error due to overstack. The last slide is for acknowledgements of AI usage. So we use AIs to check for grammar errors in the script. The code against the algorithm design part is AI generated, and recursive type examples are AI generated as well. And this is the end of our presentation. And again, thank you for all your attentions, and see you next time. Goodbye.